For AC electronic signals, the voltage V is represented using this complex number here. V0 is the amplitude of the AC voltage. J is the square root of -1. Omega is the angular frequency of the signal. We can use Euler's rule to write this in terms of sinusoidal functions. So e to the j omega t is just cos omega t plus j sin omega t. So we're interested in the real part of this if we want the voltage V at any time. Similarly for the current I, big I0 is the amplitude of the AC current. You see now why we use the letter J for the square root of -1. We don't want to confuse the letter J with the letter I, because I is traditionally used for current. Again, it's the real part of this quantity that will give us the current as a function of time. So the voltage is varying sinusoidally, and obviously the current is varying sinusoidally. When a current I flows through an inductor changes, the associated magnetic field changes also. So a changing current gives rise to a changing magnetic field. And when we have a changing magnetic field, we get a voltage V across the inductor. And that voltage across the inductor is proportional to the rate of change of the current with time. So V is proportional to di dt. Di dt is the rate of change of current with time. The proportionality constant is called L. That's a property of the inductor. It depends on the number of coils of wire in the inductor. L is called the inductance of the inductor. Now we need to get di dt, so we have to differentiate this function with respect to t. If we differentiate e to the power of something, we just get it back. But then by the chain rule, we must differentiate the power, which will give us j omega. If we differentiate j omega t with respect to t, we get j omega. So we have j omega I0 e to the j omega t. Well, you can see we're just getting j omega times little I. J omega I0 e to the j omega t is just j omega times I. Now the analog of the resistance of a resistor is the impedance of an inductor. So you probably know that V over I equals R for a resistor R. Well, in this situation, V over I is j omega L. So j omega L, this complex quantity, is not a resistance as such, because a resistance is a real quantity, but we call this the impedance of the inductor. The charge on a capacitor Q is proportional to the voltage between the plates of the capacitor V. The proportionality constant C is called the capacitance of the capacitor. Now Q is related to I. The current is the amount of charge Q passing any point in the circuit in a given time. So the amount of charge entering the capacitor in a given time is the current. In unit time is the current. So that's just dq dt. So using this equation here, dq dt is C times dV dt. C is just a constant. So when we differentiate the right hand side, we just leave the constant C to the side, and then we look at dV dt. Well, here's our formula for V. If we differentiate this with respect to time, well, we just get it back. It's an exponential. But then by the chain rule, we differentiate the power to get j omega. So we get j omega V0 e to the j omega t. Well, that's just j omega times V. So dV dt is j omega times V. Now, if we compare to V equals IR, well, if we divide across by j omega c, we get V equals 1 over j omega c times I. So 1 over j omega c plays the part of R in the resistance of a resistor. So 1 over j omega c is called the impedance of the capacitor, Z sub c. Let's look at two resistors in series. The potential across both resistors is the current multiplied by the combined resistance. Well, if they're in series, the combined resistance is just the sum of the resistances. So V in is the potential across both resistors. V out is just the potential across R2. That's the current flowing I. The same current is flowing through both of them. The same current flows through both of them. But V out is the current through R2 times the resistance of R2. We will be interested in V out over Vn. So that's IR2 over I into R1 plus R2. Now in this example we have a circuit with a resistor and a capacitor. So it's the same as the previous circuit. We just replaced one of the resistances with a capacitor. So instead of R2 in our formula for the ratio V out to V in, we will have the impedance of the capacitor, which is 1 over j omega c. We also replace R1 by R. So we'll have R in the denominator and 1 over j omega c in place of R2. Now we can multiply above and below by j omega c, so we just get 1 on top. We have j omega c times R and then plus 1 here. Now V out over V in is a complex quantity. We are interested in the square of the magnitude of this complex number, or the modulus squared of the complex number. Now the modulus squared of any complex number is the complex number multiplied by its conjugate. Now to do this calculation we need to first of all get this into, write this as a single complex number. So we have to multiply above and below by the conjugate of the denominator. You see, as it stands, we have two complex numbers. One is a complex number, and we have another complex number in the denominator. So we have one complex number divided by another complex number. So we want to write it as a single complex number. So by multiplying the denominator by its conjugate, we just get a real number down here. So when we multiply a complex number by its conjugate, we just get the square of the modulus of the complex number. So the modulus is just the square root of the real part squared plus the imaginary part squared. So it's 1 squared plus omega squared r squared c squared. The square root of that squared, so the square root goes. Okay, that's what we get when we multiply these, and when we multiply the numerators we get this here. Now we just have a single complex number. 1 over 1 plus omega squared r squared c squared minus omega rc over 1 plus omega squared r squared c squared times j. So the real part is this, the imaginary part is this. So that's V out over V in, and we have to multiply it by its complex conjugate. So we just change the sign of the imaginary part, change this minus to a plus. So this number here is the complex conjugate. So multiplying the numerators, we're just squaring the modulus of this complex number. So the modulus is root 1 squared plus omega squared r squared c squared, squaring it with no square root. So we see we cancel this on top with one of the same terms underneath. So that's the result. So that's the magnitude of the voltage ratio. Now let's look at this for this ratio for R equals 10 ohms and C equals 1 microfarad. That's 1 millionth or 10 to the minus 6 of a farad. So we have to plug 10 in for R and 10 to the minus 6 in for C, and we'll get the magnitude of the voltage ratio as a function of omega, and we can show a plot then for different values of omega. Let's look at an LC filter circuit. Now, instead of a single resistance here, we have a resistor and an inductor in series. So the resistance of these two is just got by summing the resistances. Well, the resistance of R is R. Well, we don't talk about resistance of L, we talk about impedance of L. We saw before that the impedance of the inductor is j omega L. So we need to add the impedances of these two components. So that's R plus j omega L. So that takes the place of R2 in the formula that we used in the previous example. Well, actually that takes the place of R1. If we go back up here, this is R1, appears in the denominator here. R1 plus R2 is the resistance of the components along here. So there are actually three components in our example. So R1 plus R2 will involve three terms. So we need to get the sum of the impedances of these three. So for the resistor it's R, For the inductor it's j omega L, and we saw that for a capacitor the impedance is 1 over j omega C. And R2 appears on top as well. That's R2 is now a capacitor in our problem, and its impedance is 1 over j omega C. We can simplify this by multiplying above and below by j omega C. So j omega C by j omega L gives us minus omega squared LC. Okay, j squared is minus 1, and we get a 1 here, of course, and we get j omega RC here. Alright, so that's the complex number V out over V in. Now we want the magnitude of that squared. So to do that, we need to multiply this complex number by its conjugate. Now a result I should have used in the previous example is the following. If we have the conjugate of 1 over any complex number, which I'll call Z, that's just 1 over the conjugate of Z. So if we want to calculate this quantity, and that's the type of thing we want to do actually, we have something of a complex number of the form 1 over another complex number, which we'll call Z, and we want to get its magnitude and square it. Well, what we do is we take it and multiply it by its conjugate, which we know now is 1 over Z bar. So we just have 1 over Z times Z bar. So we look at whatever number is in the denominator and multiply it by its conjugate. So our complex number is 1 over Z. It's not Z, but it's got this form. So that's what we're doing here. So Z, if you like, is this complex number in here. The real part is 1 minus omega squared LC. The imaginary part is omega RC. And its conjugate is just got by changing the sign of the imaginary part. Make this plus a minus. The real part stays the same. And when we multiply a complex number by its conjugate, it's the same as squaring the real part, which is this here, then squaring the imaginary part, omega RC all squared, and then adding them together. Now we are going to plot V out over V in as a function of omega for R equals 10. L is 0.1 millihenries. As 10 to well, a millihenry is 1,000 of a henry, or 10 to the minus 3 henries. That's 10 to the minus 3 times 0.1. Well, that's 10 to the minus 4. C is 1 microfarad. That's 10 to the power minus 6 of a farad. So we're going to plug those values in for L and C, and we're going to plug 10 in for R. So then V out over V in is a function of omega. So L, C and R are constant values. We will also see a plot for 2 other values of R, smaller values of R this time, 5 and 2 ohms. Now we're going to be interested in omega, the value of omega which maximizes the magnitude of V out over V in. So we want the value of omega that maximizes this expression. Well, this expression is maximized when the denominator is minimized. Now, omega squared R squared C squared is just a constant. Well, actually omega appears in this, but let's look at this. Let's find the value of omega that maximizes it. Well, as R approaches 0, this term drops out, and to maximize this quantity V out over V in squared, then we just set this equal to 0, and then the peak will occur at omega equals the square root of 1 over LC. We just put this equal to 0 for very small values of R. So we have the resonant angular frequency. So as you can see, as R gets smaller and smaller, the peak is occurring at a value omega, which is approaching this value here, 1 over root LC. To get the resonant frequency of the circuit, we use the fact that omega is 2 pi times f. So we just divide by 2 pi.